I'm going to take you through all of the different types of derivatives, starting with the power rule. Let's say that we're taking the derivatives. Let's do d dx of 3x to the fourth. Now, when I take the derivative with a constant multiplier out in front, I can just pull that multiplier out in front, and let's go ahead and take the derivative of x to the fourth. Here comes my power rule. The 4 comes out in front, and I'm going to subtract 1 from that power. So I end up with the answer 4 times 3, which is 12x cubed. Our power rule looks like this. So I've got d dx of x to the n is equal to, power comes out in front, and I subtract 1 from the power. Another important, really easy to apply rule is the derivative of just x. So the derivative of x is equal to 1. And finally, let's do the derivative of a constant. So the derivative of some constant, we'll call it k, is equal to 0. Let's take a look at some more derivatives applying these rules. Next, let's do the derivative of a square root. So my square root can be thought of as a power, and I'm going to rewrite this as a 1/2 power. So x to the 1/2. Now this makes it really easy. I can bring that 1/2 power out in front and then subtract 1 from the power. I end up with 1/2 x. 1/2 minus 1 is -1/2. Now I don't quite have the form that I need, so I'm going to write this as a fraction. 2 belongs in the denominator, but I'm also going to put that x to the 1/2 in the denominator as well, as a positive 1/2 power. This is going to give me 1/2. The 1/2 power is a radical x. Now this is one form of my answer, but you might want to rationalize this answer depending on what you need to do. To rationalize, I'm going to remove that square root by multiplying numerator and denominator by another square root of x. I end up with 1 times the square root of x in the numerator, 2 times the square root of x squared in the denominator. The square and the square root undo one another, and I get square root of x divided by 2 as my rationalized answer. In this next example, I've got the cube root of x squared plus 5/x squared. And I want to take the derivative, so let's put a d dx in front of there. Now for both of these, I need to think of them as powers. So I'm going to rewrite this as d dx of, let's do the cube root of x squared first. This gets rewritten, my power is 2 and my index is 3, so this is going to be the 2/3 power. I've got my plus sign in between there. And for this 5/x squared, I'm going to write this as 5x to the -2. This is going to allow me to apply a power rule for both of these terms. Okay, so here comes the derivative. Let's go ahead and do x to the 2/3 power first. 2/3 comes out in front, and it's x to the 2/3 minus 1. I'm going to deal with that in just a second. And now the derivative of 5x to the -2. I'm going to leave 5 on the outside, and I'm going to do the derivative of x to the -2. -2 comes down in front, and I get x to the -2 minus 1. Let's do some simplifying here. 2/3 minus 1 is 2/3 minus 3/3. 2 minus 3 is -1/3. So I end up with 2/3 x to the -1/3. 5 times -2 is -10 x. -2 minus 1 is -3. Now I can do a little bit of simplifying. 2 lives in the numerator. 3 lives in the denominator, but so does my x because of the negative power. This is going to be x to the 1/3 minus, in my second term, 10 belongs in the numerator, but the -3 moves the x to the denominator as an x cubed. Just a little bit more room so I can write my answer. So my answer is, I'm not going to rationalize this one, 2/3. That's 1/3 power is a cube root of x. minus 10 over x cubed. You're going to really need to have your trig derivatives memorized. I'm going to list them here. So d dx of cosine is equal to negative sine x. And then we'll do d dx of sine. So the derivative of sine of x is equal to cosine. The derivative of tangent, so d dx of tangent of x is equal to secant squared x. I've got 3 more to go. D dx of, let's do secant next. Secant x is equal to secant x times tangent x. Next is cosecant, so d dx of cosecant x is equal to negative cosecant x cotangent x. One more, let's put it up here. The derivative of cotangent of x is equal to negative cosecant squared x. We're going to apply some of these as we're looking at the product rule. Here's the product rule. The derivative of a product is equal to the first derivative times the second plus the first one times the second derivative. Here's what it looks like. So if I've got d dx of, let's say that I've got x to the 5th times the tangent of x. I can recognize this as a product, and there's a multiplication symbol there in the middle. That means that f is x to the 5th and g is tangent of x. So as I put my derivative together, I'm going to put it together as f prime times g plus f times g prime. Those primes are derivatives. Let's go ahead and start with the derivative of f. The derivative of x to the 5th is 5x to the 4th. Now I'm just going to multiply it times g. G is tangent of x. Now the plus sign. Now I go back to f without any changes. So this is going to be x to the 5th. Now I take the derivative of tangent. Its derivative is secant squared x. And this is our answer. Let's do another one. So for our second example, we're going to do d dx of, let's do sine cosine. So I'm going to do sine x times cosine of x. So I've got my function f times my function g. As I put this together, I want the derivative of f first. So the derivative of sine is cosine times g. I'm just going to rewrite that second function, cosine of x. And now my plus sign, and now I want f times g prime. So I'm going to bring down f. This is just going to be sine x times the derivative of g. The derivative of cosine is negative sine. You can check yourself by going back. Do I have the first derivative times the second function plus the first function times the derivative of the second, and that's exactly what we've got. I can clean this up just a little bit, and it's going to be cosine squared x minus sine squared. So minus sine squared x, and this is our derivative. This is our quotient rule. When I'm taking the derivative of a quotient of functions, a function divided by a function, it looks a lot like my product rule, except for this minus sign and the denominator. So I've got f prime g minus fg prime, all divided by that denominator's function squared. Let's take a look at an example. So let's say that I want to take the derivative of, let's do x squared divided by, let's do cosecant x. So I've got f as my numerator, x squared, and then g is going to be cosecant. Okay, so here I go. I want the derivative of my numerator, that's going to be 2x, and then I just write my other function, cosecant. This is all in my numerator, minus, I leave the first function, so x squared, times the derivative of cosecant. The derivative of cosecant is negative cosecant x cotangent x. In my denominator, I get cosecant x squared. So I'm going to write that as cosecant squared x. I can clean this up just a tiny bit. My numerator is 2x cosecant x plus, because I've got those two minus signs, so plus x squared cosecant x cotangent x, all divided by cosecant squared. There are some other things that you can do to clean this up, but we've got our answer here. Next, let's look at the derivative of tangent. Now, I told you to memorize this one, but this one is actually really easy to derive, and it's a great example of the quotient rule. I can rewrite tangent as sine over cosine, sine x over cosine x, and then apply my quotient rule. So as I've got it in this form, I have that f is equal to sine, and g is equal to, that's supposed to be an f, and g is equal to cosine. Here comes the derivative. So in my numerator, I want the derivative of sine first, which is going to be cosine. So I get cosine x times the denominator function unchanged, so g is cosine, minus, now I'm going to leave that first function, which is sine of x, and let's take the derivative of the second denominator function. Derivative of cosine is negative sine, and then my denominator is going to be g squared, so cosine squared x. So what do I have? In my numerator, I've got cosine squared x. Negative times negative is plus, so plus sine squared x divided by cosine squared x. Now this numerator, cosine squared plus sine squared, hopefully you remember that. That's our Pythagorean identity. That's equal to 1. So I get 1 over cosine squared x, and that's where our secant squared x comes from. Secant is the reciprocal of cosine, so that's our answer. Next, we've got our chain rule. So the chain rule acts on a composition of functions. So we're going to be able to recognize layers, and as I'm differentiating, I differentiate the outer function with respect to the inner, so I keep the inner one held, and then I differentiate the inner function. So for our first example, let's do the derivative of the cosine of x squared. So I recognize that I've got two layers here. Cosine is my outer function, and x squared is my inner function. That's what happened to the x first. As I'm differentiating, I'm going to take the derivative of the outer function, but I'm going to leave that inner function. So I'm going to take the derivative of cosine, which is negative sine, but I'm going to leave my inner function. Now let's go ahead and put the inner function in. The inner function is x squared, and I'm going to multiply by the derivative of the inner function, which is 2x. I can rearrange things just a little bit here. Let's go ahead and put the 2x out in front along with that negative sign. So I get negative 2x sine of x squared. Here comes another example. So let's do d dx of, let's do sine of 3x plus 1. So for this one, I've got my outer function. So my outer function is a sine function, and my inner function is this 3x plus 1. As I take my derivative, I'm going to take the derivative of sine first. The derivative of sine is cosine with respect to the inner function, but my inner function is 3x plus 1, so that goes here. And then I'm going to multiply on the derivative of 3x plus 1. The derivative of 3x plus 1 is just 3. Let's clean this up a little bit. Not much I can do, but I can put the 3 out in front for sure. So I can rewrite this as 3 times the cosine of 3x plus 1, and this is the answer. Next, what if we've got the derivative of, let's do cosecant squared 5x. I actually have a couple of different layers here. Let me move this one up out of the way. I'm going to recognize these layers by identifying what happened first, second, and last. Let's start with the innermost function. So what happened to x first? Well, it got multiplied by a 5. So this is going to be my innermost function. What happened next is actually the cosecant. It's really tempting to take that 2, but cosecant is going to be my middle function. And then the power 2 is my outer function. My test is if I can rewrite this one, d dx, as the cosecant of 5x all squared, and this makes it just a little bit easier. So I've got my inner function, my middle function, I'm going to call that middle function, and my outer function. Okay, here's how we deal with 3 different layers. As I'm differentiating, I'm going to go ahead and do the power 2 first. Let's do this in blue. I'm going to use just a straightforward power rule. So this is going to be 2 comes out in front, and I'm going to reduce my power. 2 minus 1 is 1. Well, what I've got on the inside here is everything else. So I'm going to go ahead and put in that cosecant of 5x. Okay, my outer function is done. Let's go ahead and do now the derivative of the middle function. The middle function is my cosecant function. The derivative of cosecant is negative cosecant cotangent. I'm going to put this in a square bracket. So it's going to be negative cosecant cotangent. That takes care of my cosecant function. I can actually cross that out. And this is going to leave me with my 5x. Let's put 5x in here as a different color. So this is going to be my 5x here and my 5x here. Finally, my last chain is to multiply on the derivative of 5x, and its derivative is just 5. I've got everything there. If you've got a really nice teacher, you can just leave it in this form. If you need to clean it up a little bit, let's go ahead and gather up our constant multipliers and that negative sign. So I get a negative 10 on the outside. I've got a cosecant 5x and another cosecant 5x. So that's going to be cosecant squared 5x. That takes care of these. And then finally I've got the cotangent of 5x. And there is our simplified answer. Let's start in with these rules and then we can move on into some examples. So first, the derivative of e to the x. This is my very favorite derivative because its derivative is just e to the x. If I happen to have a different base though, so d dx of b, so some base b, maybe that's a 3 to the x, so b to the x is equal to, I still get the exponential back, so this is b to the x. But I'm going to multiply that by the natural log of b. So I think of that as kind of a fudge factor. So these are the derivatives of our exponential where x lives up in the power. Let's also look at the derivatives of our logarithms. So I've got, let's start with the derivative, so d dx of the natural log of x. This is equal to 1 over x. But I can also have the derivative of a log base anything. So let's do log base b of x. Similar to our exponentials, it's going to be the same derivative. So I'm going to end up with, leave yourself a little more room, 1 over x. But I again have that fudge factor, and it's the same fudge factor of natural log b. Let's do some examples. So for example, let's go ahead and do d dx of, let's do log base 3 of x. This is going to be 1 over, I'm using this formula now, so 1 over x times the natural log of 3. And that is our answer. I can also apply some chain rules here as well. So let's say that I'm taking the derivative of e to the 2x. I'm going to identify my inner and outer functions based on what happened to x first. Well, first x was multiplied by a 2. This is my inner function. and then it was exponentiated base e, so this is my outer function. So this tells me the order to follow. I want to take the derivative of my outer function first. E to the whatever is e to the whatever. Let's go ahead and put that inner function in, 2x. And then I'm going to chain on the derivative of my inner function. The derivative of 2x is 2. I can clean that up and write that as 2, that's this 2 here, e to the 2x. Next, let's do the derivative of a logarithm. So let's do the derivative of the natural log of the sine of x. Okay, so again, I've got a chain rule here. I can see that layering of functions. My inner function is sine, and my outer function is the natural log. So I'm going to take the derivative of that outer function first. The derivative of a natural log is 1 over whatever happens to be on the inside. What I've got on the inside there is the sine of x. So I've taken care of the derivative of the natural log. Next, let's take the derivative of sine. I'm going to chain that on by multiplying. The derivative of sine is cosine. So I end up with cosine over sine, which you could maybe leave in this form, but this also happens to be cotangent. So I get the cotangent of x. What does that look like when I have a log of a different base? Next, let's do the derivative of, let's just do log of the square root of x. Okay, so now I'm applying a couple of different properties here. I've got the derivative of log, but I'm going to think of that as log base 10. It's my common logarithm. And yes, log base 10 is my outer function. My inner function is that square root. So I really want to rewrite this a little bit so I know exactly how to take those derivatives. So I'm going to rewrite log as log base 10. And let's rewrite that x inside the square root as an x to the 1/2 power. So x to the 1/2 power. Now I'm ready to take that derivative. So we end up with doing the derivative of our outer function first. The derivative of log base 10 is 1 over whatever is on the inside times the natural log of our base. So I've got that fudge factor, ln of 10. What was inside is an x to the 1/2 power. I'm going to chain on the derivative of the x to the 1/2 power. 1/2 comes out in front, and I get an x to the 1/2 minus 1. Okay, so what do we have? I've got 1 over, let's change that 1/2 power, this one, into a square root. So I've got the square root of x, natural log 10, times, this 2 also belongs in the denominator as well. So I've got a 2 here, and up here I've got x to the 1/2 minus 1, which is negative 1/2. I can move that into the denominator also. It's actually going to clean up quite a bit for us. And I get 1 in my numerator, square root of x, a natural log of 10, a 2, and this x to the 1/2 power is really going to be a square root of x when I bring it into the denominator, square root of x. These two right here is a square root of x squared, so that's going to give me an x. So what do I have? Let me write everything here in green. 1 is in my numerator. I've got a 2. I've got a natural log of 10, and these two multiplied together to become just an x, and this is my answer. You guys are doing really great. You're going to want to get some more practice with the chain rule though. Take a look at this next video, and thanks for watching.